Okay, so hi there, folks. Welcome to another module in number theory. This is again a course in number theory, and we are done actually with the module one. Okay, at last, with module one with the title Fundamental Properties and Preliminary Considerations. Here in module two, we're going to talk about divisibility theory and the fundamental theorem of arithmetic. So we're going to talk about the second part, the latter one, the fundamental theorem of arithmetic, towards the end, but we're going to focus more in most of this module in divisibility theory. Okay, so the division algorithm, that is the central part of the divisibility theory, is a fine application actually of the well-ordering principle, and is often employed to check the correctness of a division problem. So suppose an integer a is divided by a positive integer b. So the result will be, we will get a unique quotient, we'll call that our q, and a unique remainder, we call that our r, where the remainder satisfies the condition that it is strictly less than b, but it can be greater than or equal to 0. Okay, we call our a as our dividend, b as our divisor, and we have our quotient and the remainder. So this is actually the division algorithm, the heart of the divisibility theory. So to put that in formal writing, let's write this in a theorem, and we'll be proving that in this video. So we'll call this the divisibility algorithm. So let's call this our very first theorem in, very first theorem in module 2. Theorem, this is the divisibility algorithm, the division rather, division algorithm, division algorithm. Okay, so what does it say? So we will let a, okay, be any integer. Let's have this a in the integers, and we'll have a positive integer b. Okay, so we will put this strictly in the positive integers. You may write that as n, as a double script n as our natural numbers. Then there exists, oops, then there exists unique integers, unique q and r, which is in the integers. Okay, such that this can be written as, again, the one that I wrote above, only that in this sentence, in this manner, plus r. So we have a, okay, a equals b times q plus r. So let's name them. This a is actually our dividend. This is our dividend, our a. The b is our divisor. The q, we know this as our quotient, and r as our remainder. Oops, remainder. Okay, so this is our division algorithm. So again, we are letting a as a part of the integers, b to be strictly in the positive integers, and there will be existing two integers, q and r, which are unique, such that this algorithm will happen. Okay, so of course, the very important part before we end, where r is strictly less than b, but it can be greater than or equal to 0. Okay, so that is our remainder, because going back in our arithmetic, if r is equal to b, so it can be put as the quotient, but it should be less than b strictly. Okay, so let's give a proof of this, okay, of this theorem, the division algorithm proof. So this proof will consist of two parts. The first part we will need to establish the existence of the integers itself, so we will call that the existence proof. Okay, the existence proof, that there exists really a q and a r. And then we will also um, establish that both of them, q and r, are unique, or they are indeed unique. So we'll have the uniqueness proof. Uniqueness proof. Okay, so why do we need this? Because we say let them. If these are done, then there will be existing unique Q and R such that this happens, where R is strictly less than B, but greater than or equal to 0. So if we have this, then there's something that exists and something which are unique. So we need to prove that these are indeed existing and they are indeed unique. So let's start with our first part of the proof, which will be the existence proof. So let's have them in parts. Existence proof. Okay, so for the existence proof, we will consider the set. So consider S as our set, and this S will be composing of all A minus Bn, all numbers in this form, such that n is is an integer. Okay, and we have this number, the number here, A minus Bn in this form. A minus Bn is greater than or equal to 0. So from here, from this perspective, this n should be part of the integers, and this number here in this form should be greater than or equal to 0. So clearly, it is stated, it is, I think that's very clear to say that S, I think, no, I can't put it there. S is a subset of W, or the whole numbers. Okay, so S is a subset of the whole numbers. So we shall show that S contains a least element. So obviously, we will need the well-ordering principle there. So we shall show that S contains a least element. A least element. Okay. So to this end, we will first show that S is non-empty subset of W. So with this, we need to show first. We'll also show um, show that S, this set here, is a non-empty subset of W. Okay, so we shall show that S contains a least element by the well-ordering principle, and we will also show that S is non-empty, okay, subset of W, because we need to have it that is it's non-empty because the well-ordering principle says so. One of the conditions, it should be non-empty, and since it's part of the whole numbers, it is also proved that the whole numbers has a least element, or the well-ordering principle applies. So we shall consider two cases here. I think we will need to move one slide after because it will not fit. So for case one, let me fix my handwriting there. Case one. So suppose that A, so we will be looking at A, the dividend. Suppose A is at least 0. So then we can say that's the first case. If A is at least 0, so therefore we can say that A equals A minus B times 0. Okay, so even if n is equal to 0, okay, so A minus B, okay, is still part, or this A is still part of the S. Okay, so S, therefore, so S contains the least element here, or contains an element, not really the least. Okay, contains an element. Okay, so that's it for case one. For case two, we shall consider the opposite. Suppose a is strictly less than 0. So what shall we have? So since we shall write that since b is positive integers, or it's a natural number or a counting number. Okay, so let's put there b is in z plus or positive integers. So clearly that is b should be greater than or equal to 1. Okay, then we shall say that minus ba is greater than or equal to minus a. Okay, where did we get this? First we got that b is a positive integer because from the proof itself that b is a positive integer, and we have minus ba is greater than or equal to minus a rather, because this came from a. We know that a or b times a is greater than or equal to a because a is less than 0. So any number, of course, multiply that by a factor of a. But then if we're going to put a minus sign before them, both of them, or rather, ba is less than or equal to a. That's the correct one. Sorry. And then if we're going to multiply the whole equation by negative 1, this will revert. ba is greater than or equal to minus a. Okay? So remember that a is negative. So we start with ba is less than or equal to a, because if this is negative a or negative 2, this is negative 2, b can be 1, so they are equal. If this is 2, if b is 2, so this becomes negative 4 is less than or equal to negative 2. But notice if we're going to multiply them by negative 1, the sign will change because these a's now will become positive because there's a negative sign outside. So that's why we have it here. Furthermore, if we're going to continue, that is, we can transpose the a to the other side to have this one after. So minus ba plus a is greater than or equal to 0. Or we can simply write this as, that is, just rearrange them. A minus ba is greater than or equal to 0. And notice in this part, this is in the form of s. Okay, of s. Okay, this is in the form of a minus bn. Notice here, this is a minus ba. So you can imagine a as n equal to n. It's okay to have that. So we can see that this a minus ba is greater than or equal to 0. So consequently, we can say that um, consequently, consequently, we can say that a minus ba is an element of S. So if it's an element of S, therefore, it contains an element still. So in both cases, S contains at least one element. So in both cases, sorry, in both cases, S contains at least one element, at least one element. So S is a non-empty subset of W of our whole numbers. So S is a non-empty subset of W. I don't know if I can get that. Let's try. Okay, subset of W. There you go. Okay, so S is a non-empty subset of W. So therefore, we can say if this happens, therefore, by the well-ordering principle, therefore, thus, by the well-ordering principle, WOP, S contains a least element R. S contains a least element. We will call that our R. Okay, so since R is in S, I think we need to move here. Since since R is in S, since R is in S, an integer Q exists. Okay, an integer Q exists such that R R is equal to A minus BQ, where R is greater than or equal to 0. Okay, so we have there. So since R is in S, so there should be an integer that existing that R is equal to A minus BQ, where R is greater than or equal to 0. Okay, so since in our original statement of the proof, we say that R is strictly less than 0, but or rather R is greater than or equal to 0, but we haven't saw that R is strictly less than B. So maybe we can have a proof of that. So to show just a short one, okay, just to show that sorry, just to show that R is less than B. So to complete the inequality, strictly less than B in that matter. So we will prove this by contradiction. So assume that R is greater than or equal to B. So then we say that R minus B is greater than or equal to 0. That is by transposing this B to the other side. But we can say that R minus B is equal to A minus BQ minus B. Why did that happen? Why did that happen, sir? So we know that R is equal to A minus BQ. So we apply the R here as A minus BQ minus B. Just copy the B simply. So this is equal to, okay, moving on, A minus B, okay, BQ minus B. Moving on, by getting the B for both sides, we have A minus B, okay, Q plus 1, Q plus 1. Okay, and since this form, since A minus B times the quantity of Q plus 1 is in the form of um, A minus Bn, so let me write that. Since A minus B times Q plus 1 is of the form, is of the form A minus Bn, okay? So since it's in the form of A minus Bn, thus, simply, this A minus B times the quantity of Q plus 1 is an element of S. And also, we can also deduce that and is greater than or equal to 0. So therefore, we can say that A minus B times the quantity of Q plus 1 is an element of S. Okay? So that is, we say then, that is R minus B is an element of S because we just got this A minus B times quantity of Q plus 1 from R minus B. Remember, we got this expression from this expression here. So therefore, going back to the original one, R minus B is a part or is an element of S. So if that happens, and we know since R minus B, or rather since B is greater than or equal to 1, or we say that it's a positive integer, so therefore R minus B is less than R. Thus, we can say here that R minus B is smaller than R, okay? And it's also in S, okay? Again, R minus B is less than R, and also a part of S. So this contradicts our choice. This is a contradiction. This is our contradiction of a choice of R. So how can I say this? This is a contradiction. Again, a contradiction of our choice of R. Oops. Okay, this is a contradiction. Okay, so if since this is a contradiction, so therefore I think we can fit it here. So R must be less than B. Contrary to the R is at least B. Okay, so R should be less than B. So thus, I think to end this part of the proof, thus there exist some integers Q and R such that A equals B times Q plus R. Okay, where we have completed now the inequality, R is strictly less than B and is greater than or equal to 0. Okay, so that ends our existence proof. So we have said that there exists Q and R of this form where R is less than B, strictly less than B, but greater than or equal to 0. So I think we can end our video in this existence proof for now. Okay, thank you very much for watching.